Hey guys, so today we are going to finish up one of the last lessons. I think it's actually the last lesson of the gases unit, at least the last PowerPoint. We're going to be going through a bunch of our different gas laws. I'm actually going to separate this into two different lesson recordings because the first couple laws show up on the quiz and then the last two only show up on the unit test. So this is all going to be one PowerPoint but two separate lesson recordings. So let's get through the first couple laws. So we're going to start with Boyle's law and Charles' law, though there certainly are other laws in this lesson as well. So we're going to be going through Boyle's law, Charles' law, the combined gas law, and then in the next recording, we'll finish off with the molar volume and ideal gas laws. So Boyle's law describes the relationship between the volume and the pressure of a gas. And Boyle's law only works if the temperature stays the same and the amount of the gas, so the moles of the gas, stays the same. If that's true, then the volume will increase and drop the pressure or vice versa. So what that means is that volume and pressure are inversely proportional, or as one goes up, the other goes down. And this is because if I put pressure on a gas, I am squeezing it into a smaller volume. If I release that pressure, it will expand to take up a greater volume. The formula is down here at the bottom. It's V1 P1 equals V2 P2, which just means our first volume times our first pressure is going to be equal to our second volume times our second pressure. So let's go over how this would actually work. Okay, so for the first question, again, this is a Boyle's law question. I know that because we are dealing with volume in liters and we are dealing with pressure, in this case, measured in millimeters of mercury. Now, it doesn't matter what the pressure is measured in, as long as the pressures that we're given are the same. So I'm going to start with my formula. V1 P1 equals V2 P2. I'm then going to plug in my initial volume, which was 12.3 liters, and my initial pressure of 40 millimeters of mercury. It then wants me to know what my second volume is once the pressure has increased to 60 millimeters of mercury. So I plug it into my formula like this, and then I need to isolate my variable, my V2. So in order to do that, I just divide by 60 to move it to the other side. Since once I do to one side, I must also do to the other. And then I'll just plug this into my calculator. 12.3 times 40 divided by 60 is 8.2 liters. And that would be my final answer. So pause here, see if you can solve the second question, and then come back for the answer. Okay, so for this problem, once again, we plug in our initial volume and pressure. This time it's measured in atmospheres. And then we're given the final volume, and it wants to know what the pressure would be at that point. Again, we're just going to divide to move the 15 to the other side, and we get 0.642 as an answer. This time, because our initial pressure was in atmospheres, our answer is going to be in atmospheres. Our next law is Charles' law, which demonstrates the relationship between temperature and volume rather than pressure and volume. This time, once again, the moles have to be kept the same, so that amount of gas can't change. And then the pressure also has to stay the same. This time, as temperature increases, volume will also increase. If temperature goes down, volume will go down. So with Boyle's law, our two values, volume and pressure, were inversely proportional because as one went up, the other went down. This time, since they both move in the same direction, they both go up together or they both go down together, we say that they are proportional, not inversely proportional. And the reason that this happens is because as the temperature increases and your gas molecules heat up, they will start moving faster. They'll gain kinetic energy. They'll hit each other more. They'll bounce further apart, and they're going to take up more space. thus increasing their volume. If you cool the gas molecules down, they're going to slow down as they lose kinetic energy, which allows them to settle closer together and take up less space. So the formula for this is V1 over T1 equals V2 over T2. And let's use that to solve some of these problems together. We'll go through the first one with me walking you through it, and then you can try the second one on your own. So again, the formula is V1 over T1 equals V2 over T2. I'm going to plug in my initial volume of 600 milliliters. It wants to know what my second volume is going to be. And again, that's going to come out in milliliters. If I put this in as liters, it would come out as liters. And you might remember from our previous lesson that I said when dealing with temperature in gases, we should always convert to Kelvin. It's not going to matter in all of the problems, but with some of the formulas, it becomes crucial that you're using Kelvin. So as a general rule, just always convert your temperature to Kelvin. So I'm going to go off to the side here and I'm going to convert my 20 degrees Celsius into Kelvin by adding 273.15. 20 plus 273.15 is 293.15 Kelvin. So I'm going to plug that in. And then I'm going to do the same thing with my second temperature. And that's 333.15 Kelvin. Now, in this case, there's two different ways that we can go about solving this. We can either solve it algebraically, in which case we would multiply by 333.15 and then multiply the whole other side by that as well, which is definitely an easy option, or you can cross multiply and divide. So in this case, I'll show you how to solve it algebraically, which is a good option if your variable that you're looking for is on the top. If the variable you're looking for is on the bottom, then cross multiplying and dividing is definitely an easier option. And you can certainly just always cross multiply and divide if you find it easier. But anyway, I need to isolate my V2, so I'm going to multiply by 333.15. That cancels out. And then I take the whole other side and multiply it by 333.15. And then in my calculator, I'm just going to do 600 divided by 293.15 times 333.15, and I get 681. Oopsies, yeah, 81 milliliters. Okay, so I would like you guys now to try the second question and then come back for the answer. And sorry, I also rounded this last one on. There should be a 0.8 there. Anyway, as we go into the next question, again, I plugged in my initial volume over my initial temperature divided by my second volume, and I'm trying to find my second temperature. Now this time, because my variable is on the bottom, I would have to multiply by T2 to move it to the other side. It's actually easier to just cross multiply in this case, or at least I find it easier. So T2 times 2 is just 2T. And then 1 times 293 is, of course, just 293. And then we just divide by the 2 to isolate our T. So 293 divided by 2 is 146.6. And that would be in Kelvin, of course. And then if you had to convert back to degrees Celsius, I would just do 273.15 minus my Kelvin. 273.15 minus 146.6. And I get 126.55. Okay, so that is how much, that's what my new temperature is. And actually, sorry, before I do that, it doesn't just want what my new temperature is, it wants the decrease in temperature. So I started at 293.15. I will subtract the 146.6 from that. So 293.15 minus 146.6 is 146.55. And then I can convert that decrease in temperature into degrees Celsius. So this is step 1, that's step 2. Step 3 is do 273.15 minus 146.55. 273.15 minus 146.55 equals, there we go, 126.6. Okay, that is all for Charles' law. Next up, we have a law called Gay-Lusak's law, which describes the relationship between temperature and pressure. Again, in this case, the amount of gas, or the moles, have to stay the same, and so does the volume, so the amount of space the gas is taking up. Gay-Lusak's law tells us that as temperature increases, pressure will also increase. If temperature went down, the pressure would also go down. So once again, just like with Charles' law, these two values are proportional to each other. They go up together, they go down together. This is because as the gas molecules heat up, they will, of course, gain kinetic energy. They will move faster. They will collide more forcefully, not only with each other, but also with the sides of the container, thus putting more pressure on the container. And so our formula is P1 over T1 equals P2 over T2. Again, we'll go through one of these questions together, and then you guys can try the next one on your own. Okay, so in this case, again, we're going to start with our formula. I'm going to plug in my initial pressure, which in this case is 104 kilopascals. And then my second pressure is 96 kilopascals. My temperature, right now it's in 32 degrees Celsius. I'm going to add 273.15 to get it into Kelvin. And plug it into my formula. And then I'm looking for T2. Again, I'm going to cross multiply this time because I find that easier and my variable is on the bottom. T2 times 104 is just 104 T2. And then 305.15 times 96 is 29294.4. And then, of course, I have to divide by 104 to get my T2 by itself. So that's 281.68 Kelvin. Now, once again, it's not asking for my final temperature. It wants to know what the temperature change is. So I'm going to go off to the side again, and I am going to say, okay, I started at 305 Kelvin. Now I'm at 281.68. Let's see what the difference is there. And that is a difference of 23.47 Kelvin. Okay, so please try question number 2. Okay, so for the second question, I'm looking for my initial pressure. I plug in my final pressure of 2.1 atmospheres. I also plug in my initial and my final temperature, both in Kelvin. And then in this case, I solved algebraically since the variable that I'm looking for is on the top. I just find it easier. Again, you could cross multiply and divide again here and still get the same answer. But I just multiplied both sides by 318.15, and I get 2.42 atmospheres as my final answer. Okay, the last law that we're going to be going over today essentially just combines these different laws together to show the relationship between pressure, temperature, and volume all at once. But once again, we do still have to keep the amount of the gas or the moles the same. Our formula is P1V1 over T1 equals P2V2 over T2. So let's try one of these practice questions. Okay, so I'm going to start with my combined gas laws formula. I know that this is the one that I need to use even without the title at the top of the slide because I'm given pressure, which is my atmospheres. I'm given temperature in Kelvin, and I'm given volume in liters. So as soon as I see all three of those, I know that the combined gas law is the one that I'm going to need to use. Just so you know, on a tester quiz for all of these problems, it's not going to tell you which formula to use or what law you're dealing with. You have to figure that out just by looking at what variables you're given, what values you've been given. And then those values will determine which formula you use. Anyway, I'm going to plug in my 2 atmospheres of pressure, my 300 liters of volume with my 200 Kelvin of temperature. And then my second pressure is 0.25 atmospheres. I'm looking for my V2 and my second temperature is 400 Kelvin. Again, there's a couple different ways that you can solve this. You can cross multiply, you can solve algebraically. I'm going to solve algebraically. Again, that's the way I find easier when the variable I'm looking for is on the top. So the first thing I'm going to do is I'm going to just solve this entire left side all at once. So 2 times 300 divided by 200 is 3. And then I'm going to move my 400 to the other side by multiplying. And that is 1200 equals 0.25 V2. And then, of course, I just divide by 0.25 to move it to the other side. And I get 4,800 liters as my V2. I know that this is in liters and not milliliters just because the original volume was given to me in liters. Okay, so the next one's a little bit wordy, but there will be some questions like this on your tests and quizzes and stuff. So read through this and see if you can solve it. Pause here and then come back when you're done. Okay, so this question is very wordy. First thing I see is that I've got a temperature in degrees Celsius. So I add 273.15 to get 305.15 Kelvin and then plug that in. It also says that the atmospheric pressure is 101 kilopascals and that my lung capacity at that point is 2.4 liters. Then it says when you dive down, the pressure is 141.2 and my lung volume decreases by 0.74. Now you'll notice that it says decreases by 0.74 and not becomes 0.74 liters. So I go off to the side here, I take the lung volume I started with, decrease it by 0.74 by subtracting 0.74 and get 2.66. So that is the lung volume at the bottom of the lake. That is the number that I plug in here. I also plug in that pressure, and then again, I'm solving for my temperature, my T2. When the variable I'm looking for is on the bottom, I like to cross multiply. So when I do that, I get this big blue line here. And then in order to isolate T2, I divide by 2.4 times 101.3. And then I plug that all into my calculator and get 294.2 Kelvin. But it did specifically ask for my temperature in degrees Celsius. So I subtract 273.15 and get 21 degrees Celsius as my final answer. Okay, so that is going to be it for this recording. We'll come back and finish going through this lesson in the next recording. But if you have any questions about these ones, please let me know.